guys, this is lesson 2.4. It's called solving equations with the variable on each side. But there's sort of a hodgepodge of things just to talk about in solving equations. So let me try to highlight a few things from the textbook. If you want to follow along, the lesson starts on page 97, but I'm going to be working some problems from page 100. All of the examples in the actual lesson, you could look through them yourself. A good study technique is to look at the very beginning of an example, see if you can work it yourself without looking at the answer, and then see if you did okay, or maybe you got stuck somewhere, and then go back and look at the example. That's a great way to read a math textbook. I'm going to work some problems that you don't necessarily have worked out for you already. If I'm looking at problems 1 through 8, these are some various math problems with some different kinds of answers that come up. So let me start with something like, well, let me just do number 1 and get us going. So here we have some choices, really. We want to get our x's together. We don't want x's in two different places. And then we want to get our constants. Those are the numbers that don't have x. We want to get those together as well. So I actually have 4 choices here. I could subtract 13x, I could subtract 2, I could subtract 4x, and I could subtract 38. I could do any of the above. And I will end up with the same answer if I do it correctly. So I'm just going to start with, I'm going to just minus 2 for fun here. There really was no reason why I picked that. All right, now I'm seeing a little clearer that I want to get my x's together, and I think I want this one to move over here, because if I were to subtract 13x now, I would end up with 0 over there on the left, and I would still have this number hanging out over here with the x's, so it doesn't really get me where I want to be as quickly. None of those things are wrong. Sometimes you might work an extra step if you don't maybe do it the trickiest way, but that's fine. I'm going to subtract 4x here. That will give me a 9x over here, and that equals 36. I need to get x by itself, so I'm going to undo this times by dividing and get x equals 4. All right. Number 2 looks pretty messy with all those fractions, but I'm actually going to move to number 3 because it has parentheses. By now you might have heard of the distributive property, and that's where we would take this 6 and multiply it by each thing in the parentheses to undo the parentheses, but there's actually a faster way to do this. Since we have 6 times n plus 4, if you think of n plus 4 as just one chunk, we can take this whole thing right here, as we really just have 2 things multiplied together, 6 times this little group n plus 4, and I'm going to divide the whole thing by 6. So if I do that, the 6's will cancel just like that. I have to do that on the other side, but the neat thing that happened on the left is now all I have is n plus 4, and the parentheses really don't matter once it's isolated. Negative 18 divided by 6 is negative 3. And then I'm going to finish out by subtracting 4 here to get n all by itself. All right, once we get to number 5, we start to see something kind of weird. We're just minding our own business, solving some math, and I'll show you what happens. Okay, way out here is this 5. Is that what I want to do? Get that. That's kind of a weird one, but let's go ahead and do that, minus 5. The reason that's weird is because 2n and minus 5, they are not like terms, and they can't go together, so they end up doing this. Okay, I could go ahead and divide by 2, just like we did in the last problem, but in this case, I'm going to go ahead and do the distributive property. The reason being is I'm seeing something weird happening. I don't really want to draw this line and divide by 2, because look how messy it is on the right. So I'm going to do the distributive property. 2 times n is 2n, and 2 times 1 is 2. Do you see anything weird yet? 2n plus 2 is the same thing as 2n minus 5. Well, 2n is going to be the same thing no matter what. But you can't take one thing and add 2 to it and have it equal the same thing when you subtract 5 from it. So this is odd. It actually can't equal itself. But let's say I went a little bit further. Watch what happens. Let's say I minus 2 from both sides. And now I have 2n equals 2n minus 7. Well, that looks pretty weird, right? How can 2 times something equal 2 times something minus 7? Well, let's say I subtract 2n. Now I have 0 equals negative 7. Well, it does not. It does not equal negative 7. And so if you get an untrue statement, what we're going to say is there is no solution. Right? Number 6 there, if you work it out for yourself, has no solution also. So you should try it and see what happens. I'm going to move on to number 7 because it's another weird one. 14v plus 6 equals 2 times 5 plus 7v minus 4. Well, it's kind of cumbersome just like that. Let's add 4 here. Let's just tidy things up a bit. 14v plus 10 equals 2 times 5 plus 7v. All right, let's go ahead and use the distributive property and undo this. 2 times 5 is 10, and 2 times 7v is 14v. See anything familiar? Look, 14v and 10. It's just written backwards. In fact, I could say 14v plus 10 equals 14v plus 10. Well, it's the same on both sides, completely. Look at that. So let's say I don't see it, and I keep going. Let's subtract 10. I get 14v equals 14v. Interesting. Maybe I even want to subtract 14v. Seriously, I'm being a little foolish. 0 equals 0. Well, yes, 0 actually does equal 0. And so if I get a true statement, what that means is I have something called an identity. It means that in the beginning, we couldn't necessarily see it, but this equation is just another form of this equation. They equal each other exactly. So all real numbers are solutions. So there are infinitely many solutions to this. Don't worry about the word real. That's a kind of a technicality that we'll get to later. In fact, we don't really deal with that word a whole lot until Algebra 2. But when we have an identity, when we have a true statement, I just want you to think all numbers are solutions. All numbers are solutions. As opposed to this one, where we had an untrue statement, and then we said no solution. Okay? True statement, infinitely many solutions. We say all real numbers are solutions. Untrue statement, no solution. All right. There's a bunch of equations in 10 through 21, and if you want to work out any of those yourself for practice, just send me a message and I'll take a picture of the answers for you. It's important here. Let's jump down to another mean one. What if I have 2x equals 2 times x minus 3? There's a fine line here between getting no solution, all numbers, and just making a math error. You gotta be careful. All right, here's one of these where I wouldn't probably bother to do the distributive property to do 2 times x and 2 times negative 3. I'm just going to divide by 2 because that'll cancel these 2's. I can do that because this is times. These are just factors. So I'm just dividing by 2, which means now I have x equals x minus 3. So that's a lot simpler, right? But we're going to get into trouble when we try to get our x's together. X minus x is 0, and then I get negative 3. That's about the time I usually go back and check my numbers because that looks so strange. But I got an untrue statement, right? 0 does not equal negative 3, so there is no solution to this. Thankfully in Alex you're going to get instant feedback on whether or not you did that right or wrong. I'm going to solve number 27. Negative 5, 3 minus q. Remember, you can pause. It's a lot more fun if you get to try it before you watch me do it. So you try it and see what you get. You might do it a totally different way. I'm going to subtract 4. Interesting. And this is kind of fun. I could divide by negative 5. I'm actually going to show you what happens if I try to divide by negative 5. I would have to divide everything by negative 5. So since it's 5 times that, that's a factor, and I can do that. If I want to divide by negative 5 over here, here's a mistake that people often make. I have to divide each piece by negative 5. So it's actually as if I did this, 5q over negative 5 minus 15 over negative 5, right? Or plus a negative 15 over 5. So I'm going to get over here 3 minus q equals, and then these cancel. But watch out, there's a positive on top and a negative on the bottom. So I end up with this negative q. And then I have this negative 15 divided by negative 5, so I get plus 3. Now this looks really strange, but if you just rearrange it a bit, you could say this, 3 minus q equals 3 minus q. And so it's a true statement, right? They equal each other, they're exactly the same. If I keep going, let's say I add q to both sides, subtract 3, I'm going to get 0 equals 0. You don't have to go that far because we can certainly see that this is identical. It is an identity. It means that in this original equation, this was another way of writing this. And so since this is a true statement, then we're going to say that all numbers are solutions. There are infinitely many solutions that work there. It means you can plug in any single number for q and it works. There's your lesson. I'll record a part 2 with some Alex examples for you.